Hello, hello, hello. A new greeting this time. We've already talked about independent and dependent samples. And in this video, we're going to go through another example of an independent samples hypothesis test. So the context of the problem is exercise physiology. So an exercise scientist wishes to compare two fitness programs, and these are designed specifically for women. 80 women that exercise regularly are selected, and 40 are randomly assigned to, there's an older program, program 1, and 40 of the participants are assigned to the newer program, program 2. After 18 weeks in the two programs, each woman is given a fitness test that yields a score of between 0 and 100. So the question is, do the data provide evidence that the mean fitness score for those using the new program, program 2, is greater than that of the older program? So the first step in any problem when you see a two sample problem like this is just to sort of make sense of the groups. Group 1 are the 40 women, that are assigned to program 1. Group 2 are the 40 women assigned to program 2. Are these independent or dependent? That's the first question you should ask, since the selection of women for program 1 is unrelated to the selection of program for women 2, which means that essentially the data are not paired in any way. We don't pair up woman 1 with woman 2 in the program and woman 2 with woman 2 in the two programs. So because the selection of the samples are unrelated, the groups are independent. So what we want to do, the question of interest is, do the data provide evidence that the mean fitness score for all those using the new program is at greater than that of those using the older program? Use alpha equals 0.05 as your level of significance. So the means we're going to compare. Mean 1 is the mean fitness score, it's the test score, of all women using the old program, program 1. Mean 2 is the mean fitness score on that fitness test of all women using the new program, program 2. The null hypothesis, being the skeptic's hypothesis, is that there's no difference in the mean scores. All women, essentially the mean score of all women using program 1 equals the mean fitness score of all women using program 2. And the way a computer views that is they view it as differences. If the two means are equal, that means when you subtract them, mu1 minus mu2, it equals 0. The alternative, you want to know if essentially the score of those using the new program, group 2, is greater than that of the score of women using group 1 or program 1. So mu1 would be less than mu2 for this hypothesis. The decision rule is to reject H0 if the p-value is less than 0.05. That's the level of significance. And now getting into a little bit of the whys behind this. Here are our hypotheses. And so mu1 minus mu2 equals 0 versus mu1 minus mu2 is less than 0. Again, the computer turns it into a difference. If the validity conditions are met for each sample, and the null hypothesis is true, then the mean of the sampling distribution of the sample means is equal to mu1 minus mu2. And we think if they're equal, that equals 0. Using this and the standard error of the difference in the x1 bar minus x2 bar, we come up with a test statistic. And the test statistic is the difference in the sample means, which is right top, over the standard error of the difference in the sample means. This is a t-curve for the difference in the sample means, x1 bar minus x2 bar. If the null hypothesis is true, those should be about 0. Again, we're looking for evidence that mu1 minus mu2, the difference is less than 0. So this is going to be a left-tailed test. We're looking for evidence that the difference is less than 0. Okay, so using a statistics package now, which was what we're going to be doing with the independent samples test, we want to determine this p-value, which is this value right here. Okay, and that is the p-value is the likelihood or the probability of obtaining the observed test statistic or t-score, or something even more extreme, sort of more farther from the mean, if the null is true. So to do that on StatCrunch, I have the data here, program 1 and program 2. Go to Stat. It is a t-statistic. It is 2 samples independent, and we have the data. Okay, so the program always does sample 1 minus sample 2. Now remember, we did mu1, program 1, minus program 2. So sample 1 is going to be the scores for program 1. Sample 2, the scores for program 2. Scroll down, we're doing a hypothesis test. The mean of the differences is 0 versus the alternative that the difference in the means is less than 0. And compute. And that gives you the statistics for the hypothesis test. Now, on StatCrunch, okay, I have copied those values here. I'll just interpret these a little bit. So what we have is we're looking at the difference in the sample means. The sample difference is the difference in the sample means, x1 bar minus x2 bar. The standard error is in that test statistic is the bottom portion. What we want to focus on is the t-statistic. This is the value of the test statistic, negative 3.19. That says essentially that our sample difference, negative 9.15, is about 3 standard deviations less than that mean. And we look at the p-value of 0.0014. That is the probability of seeing a sample difference of about negative 9, assuming that the null is true, that the means are truly equal. All right, so what we have is these hypotheses, a p-value of 0.0014. The level of significance is 0.05. So our conclusion, since that p-value of 0.0014 is less than 0.05, we reject H0. So that says that there is evidence, and let me bring up my pen. There is evidence that the mean fitness score for all women using program 2, essentially what we're saying is that the mean scores for program 1 are less than the mean scores for program 2, which is the same as saying that the mean scores for 2 are greater than the mean scores for 1. So we can say that the mean fitness score for all women using the new program 1, or 2 rather, is greater than the mean fitness score for all women using program 2, which means program 1. Let me see if I can say that again. The mean score for all women using program 2 is greater than the mean score for all women using program 1. The last question about this is validity. So going through the validity of this process, we have 2 samples, 40 women using program 1, 40 women using program 2, randomly assigned. They are independent, we've already decided. The women were randomly selected for participation in program 1 or 2. Notice the 80 women weren't necessarily randomly selected, but when they came to the experiment, quote unquote the experiment, they were randomly assigned to program 1 or program 2. That, by the way, is called a randomized design. Okay, so the women were randomly selected for participation in the program. The sample sizes N1, the group 1 is 40, is greater than 30. N2 is 40, is also greater than 30. Just as an aside, again, if either of these sample sizes were less than 30, then what we would need to do is go to, let me bring up the, let me bring back our StatCrunch results. We would need to go to StatCrunch and take a look at the graphs of program 1 and program 2. I'm going to compute those. And here is the test scores for program 1. Notice they look roughly symmetric. The test scores for program 2, they also look roughly symmetric. So even if our samples were less than 30, if we examine those sample histograms, they would suggest that the fitness scores for all women would be normally distributed. Okay, in this case it doesn't matter because our sample sizes are greater than 30. Lastly, the standard deviations of the fitness scores for all women using program 1 and program 2 are unknown. Those are our validity conditions for the independent samples test. So that says that the procedure, the independent samples hypothesis test for this difference in means is valid.